All right, people. I believe everybody is doing great, nice, and absolutely fine. So please let me know in the chats if I'm perfectly audible, visible to each and every single student. Okay? Everyone means everyone. Let me know in the chats and call up your friends because we are starting the new chapter that is electromagnetic induction. Okay. I would want all of you to call up your friends so that we can start this journey. We can start the new chapter over here. Everybody, everyone means everyone. And most importantly, if you have not liked this session yet, I would want you guys to hit the like button as soon as possible because liking the session is extremely mandatory. So I would want you guys to hit the like button as soon as possible. Okay, guys? Make the like count to 100 plus right now. Okay, in next 5 seconds. 5, 4, 3, 2, 1. And now it should be 100. It should be 100. Okay. Everyone guys. Cool. So let the people come and we are starting this particular session. Okay. And I would want everybody of you to tell me how is everything going? How is everything going? Tell me. Everyone means everyone. Everyone means everyone. Okay. So guys, every single thing will be starting from the scratch. Okay. Let me just tell you first and the foremost thing out there. What is that? I know there are a lot of Phoenix Pro aspirants, Phoenix Pro students, okay, who are joining this particular batch, okay, in this particular chapter. Now, what I would want you guys to understand is one thing. They'll say, sir, since you are starting from EMI, electromagnetic induction chapter, is it possible for us to understand each and every single thing? Let me just give you the guarantee, okay? I am giving you the 100% assurity that you would be able to understand each and every single thing. That is my guarantee, okay? Even if I start from this particular chapter. You don't have to worry about anything. If you haven't studied this chapter before, no problem at all. So if you are learning this, if you are studying this for the first time, you would be able to understand each and every single thing because we start each and everything from the basics, from the scratch, and we take you to the level which you actually need, which you actually want. Okay. So, my dear people, I would want you guys to hit the like button as soon as possible. Okay. Now we are starting. Let's basically start our chapter. Let's basically start our journey. So the first topic that we need to understand over here is that is magnetic flux. Since you guys have studied the electrostatic flux previously, electric flux. In magnetism, we studied the magnetic field and all, and right now we are going to talk about the magnetic flux. Guys, understand one thing. Listen to me very carefully. Let's suppose I have told you, let's suppose I have got a magnet over here. I would want all of you to understand this very carefully. Let's suppose I have got a magnet over here. Sir, if this is a magnet, we know that this magnet creates the magnetic field. And if in that magnetic field you place something, we know that, sir, it will be attracted or something like that. Now, what I want you guys to understand is that if you remember, if we have got a magnetic field over here, sir, if we have got a magnet over here, we know it will create the magnetic field, and we say we represent that magnetic field with the help of the magnetic field lines. If you have to show that this magnet is creating the magnetic field, we represent that magnetic field with the help of the magnetic field lines. What does this say? This says that a magnet creates magnetic field. Like if I say I have got a charge over here, we say, sir, this charge creates the electric field lines. Similarly, we know that the magnet creates the magnetic field lines. Yes, sir, we know this. Okay. Now see, let's suppose, my dear friends, there are some magnetic field lines which are coming something like this, These are the magnetic field lines. Sir, where does these magnetic field lines come from? Let's suppose you have placed some sort of magnet over here. Because of that magnet, we say these field lines are coming out, or this magnetic field is being created because of that magnet, Okay. Now understand very carefully, my dear friends. Let's suppose I place a sheet over here in front of this. This is the magnetic field and this is the sheet and it is having the area A. Okay. Now tell me one thing. How many number of magnetic field lines are crossing the sheet? Like these are the magnetic field lines coming and you have got the sheet over here. These field lines are crossing the sheet perpendicularly. I am asking you how many number of field lines are crossing over here. We say number of field lines crossing. How many number of field lines are crossing this area? We say, sir, 4 field lines are crossing the area. Okay. Let's suppose I say we have got over here another case. Okay. Let's place the strong magnetic field over here. Let's place a bigger magnet over here. Because of the bigger magnet, we say there are large number of field lines which are coming out. That's why density of field lines is more. And I'll place the area over here. I'll place the same sheet exactly over here. How many number of magnetic field lines are crossing this particular sheet? How many number of field lines are crossing this particular sheet? You say, sir, 1, 2, 3, 4, 5, 6, 7. So here, number of field lines crossing, are basically 7. My dear friends, here number of field lines are crossing are less, here number of field lines crossing are more. I can say, sir, this magnetic flux here is 4 and I can say magnetic flux here is 7. Sir, why? Because the number of field lines crossing the surface is what we call the magnetic flux. If more number of magnetic field lines are crossing, we say magnetic flux is more. If less number of field lines are crossing, we say magnetic flux is less. If you remember the concept of electric flux, that was number of electric field lines crossing the surface. Here we have number of magnetic field lines crossing the surface. Guys, tell me in the chats, is this crystalline clear? Tell me in the chats, is this crystalline clear? And most importantly, my dear friends, I would want you guys to hit the like button as soon as possible. Okay. So we say in this particular case, flux is 4 and flux is 7. Now, can I define this flux? I'll write over here. It is the number of magnetic field lines. It is the number of magnetic field lines crossing the surface perpendicularly. Number of magnetic field lines crossing the surface perpendicularly is what we call the flux. Okay. Now guys, one more thing I just want to tell you over here. What is that? See. Let's suppose, my dear friends, I say I have got this area over here. And these are the field lines which are exactly crossing the area. What I would want you guys to understand is that, tell me, if I say the stronger is the magnetic field over here, will the flux be more or less? Sir, stronger is the magnetic field, we say more number of field lines will cross. See, here magnetic field is stronger, we say more number of field lines are crossing. Here magnetic field is weak, less number of field lines are crossing. So can I write in that particular case, sir, when it comes to this magnetic flux, it is directly proportional to magnetic field. Stronger is the magnetic field, stronger is the flux. Stronger, more will be the number of field lines crossing. Okay. Now guys, see, if I place the bigger area, let's suppose I'll make a small area over here. I'll basically place a small area over here. Guys, through this small area, how many field lines are crossing? 1, 2, 3, 4. This one is not crossing. This one is also not crossing. So if you decrease the area, what do you think? What is going to happen with the magnetic field lines? We say, sir, less number of magnetic field lines in that case will cross. So we say flux in that case will decrease. So can I write? When it comes to area, I say magnetic flux is directly proportional to, we say, area. More is the area, more is the magnetic flux. More is the magnetic field, more is the magnetic flux. Can we combine these two equations? We say combine the two equations. If we combine the two equations, can I write, sir, this magnetic flux is simply equal to, that is B dot A. Sir, B dot A. This is, more is the magnetic flux, more is the magnetic field, more is the magnetic flux. More is the area, more is the magnetic flux. So this will be the formula in that particular case, Okay. That is, we say flux is equal to B dot A. Okay. Yes, sir. Till over here it is clear. Now guys, understand one more thing over here. Sir, what is A dot B? A vector dot B vector. Sir, it is AB cos theta. What is B dot A? Can we not write over here phi B is equal to? I can say this will be simply, that is BA cos of theta. And I say where theta is the angle between, we say B and A. Theta is the angle between magnetic field and area vector. Sir, why are you confusing over here? If magnetic field is more, flux is more. Agreed, 100% agreed. If area is more, magnetic flux is more. 110% agreed. Sir, what is this cos theta? You are putting the cos theta in this equation. This is getting out of my mind. Now, let me tell you. My dear friends, listen to me very carefully. Let's suppose, I say I have got a sheet over here. Always remember, guys, this sheet has got the area, length into breadth, okay? Guys, could you please tell me, is the area vector quantity or it's a scalar quantity? Sir, we know area is a vector quantity. So vector quantity has a direction. If I say this board over here, it has area. What is the direction of its area? That is perpendicular to this surface, perpendicular to this board. Sir, what is the direction of its area? That is perpendicular to this sheet, Okay. Now. Let's suppose we say I have got a sheet over here. Understand very carefully, my dear friends. Okay. And in this particular case, if I say magnetic field is something like this. This is the direction of magnetic field. And we say here it is at angle, we say theta. Here magnetic field is crossing at angle theta. Could you please tell me how many components of magnetic field does it have over here? Sir, if this is B, we can clearly say this is B cos of theta. If this is B, we can clearly say this is B sine of theta. This is B cos of theta, this is B sine of theta. And when it comes to area vector over here, we know, sir, area will be perpendicular to this. Area will be perpendicular to the sheet. Guys, tell me one thing. Which component of the magnetic field is crossing the area, is crossing the sheet? Sir, B sine theta is just touching the sheet. B cos theta is crossing the area. So the one which crosses the area will contribute to the magnetic flux, will create the magnetic flux. Like if you take a look over here, sir, all of these magnetic field lines are crossing the area. What is the definition? It is the number of magnetic field lines crossing the surface perpendicularly. So can I say over here in this particular case, I say here B sine theta will not contribute to flux. B sine theta will not contribute to flux. Why? Because B sine theta is not crossing the area. Which one is crossing the area? We say B cos theta. Okay. Now guys, we say if we have to write the magnetic flux over here, magnetic flux here will be, sir, magnetic field multiplied by area. What is the magnetic field over here? That is B cos of theta. And what is the area over here, sir? That is A. So can I write this as that is BA cos of theta? That is the reason you have got cos theta in this particular equation. Guys, please let me know in the chats with the fire emojis if everything is crystal clear and sorted. Everybody, everyone means everyone. All the people out there, let me know in the chats if this is crystal and clear to each and every single student. Come on guys, tell me. And if you have not liked this session yet, I would want you guys to hit the like button as soon as possible. Everyone, give me the signal in the chats. I'm looking at your comments, okay? Okay. Okay. Now let me give you a very good question over here. Guys, see, all of you. Let's suppose we have got a plate over here. Okay, this is a plate which has the area. Let's suppose we have got a plate something like this. Yes, this is the plate that we have got. Okay. And in this particular case, guys, listen to me very carefully. This is a plate that I have exactly over here. And I am saying that magnetic field is crossing this plate something like this. Magnetic field is crossing this plate something like this at an angle, we say, sir, theta. At an angle theta with the horizontal. You guys are supposed to tell me, the question is, find the flux, find the magnetic flux through the plate. Find the magnetic flux through the plate. You guys are supposed to tell me, find the magnetic flux through the plate. You say, sir. Guys, see. This is the magnetic field. This is the angle theta. Can I say this magnetic field will have two components? This magnetic field will have two components. Sir, first one is this. This will be B cos of theta. And second one is this, and this is B sine of theta. B cos of theta and B sine of theta. Cool? Absolutely cool. Now tell me guys, in this particular case, this will be the area vector. This is the direction of area vector. Area is this. Tell me, which of the components over here is crossing the surface? Which of the components over here is crossing the surface? Could you please tell me? Sir, B cos theta is not crossing the surface. It is just touching the surface. It will not create the flux. But B sine theta is crossing the surface. I say here I'll write B sine of theta is crossing the surface. Okay. I say in this particular case, we say B sine theta is crossing the surface. Now, if I have to write the flux over here, can I say here magnetic flux will be simply, that is, I'll write B sine theta, that is B sine theta multiplied by area of this is, let's suppose A. Area will be pi r square, let's take it A. Area will be A. So can I say this will be BA sine of theta in this particular case? Means it is not always cos component. It is that component which crosses the surface, which crosses the area. We have to take that component only. And even if you check it with this method, see guys, you say, sir, I'll write flux over here. phi is equal to, that is BA cos of theta. Sir, I'll use the general formula. I say no problem, use it. Guys, if this is theta and whole is 90, could you please tell me what is this angle, sir? This is 90 minus theta. Okay, yes. Now, can I write over here, sir? We say flux is equal to, that is BA cos of. Now, guys, what is the angle between magnetic field and area? This is area. This is magnetic field. That is 90 minus theta. What is the angle between magnetic field and area? Because theta is the angle between B and A. Sir, that is 90 minus theta. 90 minus theta. So can I say in this particular case, cos of 90 minus theta is what? That is sine theta. So I'll write BA sine theta. So by using this method also, we are getting the same answer. By using this method also, we are getting the same answer. Guys, do you all agree? Please tell me in the chats. Do you all agree? Please tell me in the chats. Everyone means everyone. Everyone means everyone. Everyone means everyone. Guys, great. Now see. Next thing I would like to tell you over here. Find the magnetic flux through the ring. Find the magnetic flux through the ring. We have got, find the magnetic flux through the ring. We have got this ring over here. Guys, we have got this wire over here. This is a wire. Okay. And current is flowing through the wire. Guys, always remember this. I have taught in magnetism, but for Phoenix 4.0 for Phoenix Pro students, guys, see, we say if this is a wire, and in this wire current is flowing. I have got a wire and current is flowing. Always remember, sir, a current carrying wire produces the magnetic field. Sir, it will produce the magnetic field around it. Okay. Like here it will produce the magnetic field. How to find the direction of that magnetic field? Guys, see. This is the wire. I say place your thumb along the direction of current. And curl your fingers at the point where you have to find the magnetic field. So here it is pointing inwards. So magnetic field because of this wire at this point is inwards. A current carrying wire always produces the magnetic field. Now, because of this wire, what is the direction of magnetic field from this side? Place your thumb along the direction of current. Okay. And then curl your fingers. Here it is pointing outwards. So here it is magnetic field is outwards. Here magnetic field is outwards. Now see guys, in this particular case, I would want you guys to understand. If we have got a wire, in this wire, current is flowing in the upward direction. Okay. And this is the ring which is placed over here. We have to find the flux through the ring. Guys, see, I say, place your thumb along direction of current, magnetic field here will be inwards. So from this side, magnetic field is inwards. Okay. Guys, see. Now, place your thumb along direction of current. From this side, magnetic field through this coil will be outwards. Through this area will be outwards. So we say the number of field lines which are going in from this side, right side, is equal to the number of field lines which are coming out. So I'll write through the ring, number of field lines, going in will be equal to number of field lines coming out. So if that is the case, we say net magnetic flux in that case will come out to be 0. If the number of field lines going in will come out to be the number of field lines coming out, we say net flux through this will be 0. Individually from this side it is not 0. But net magnetic flux will be, in that particular case, will be taking it 0. Okay. Now, can you tell me, will the flux be 0 over here through this ring or non-zero? The question is same over here. I'll ask the same question. Find the flux through the ring. Through the ring. Find the flux through the ring. Guys, see. I say because of this wire, magnetic field here will be inwards. Magnetic field through the ring will be inwards. Okay. So in this particular case, the complete magnetic field is inwards. The complete magnetic field is inwards. So I say here magnetic flux is not equal to 0. Here magnetic flux is not equal to 0. It is non-zero. Why? Because here the field lines are only going in. Let's talk about this question. It is like the wire is placed something like this and there is a ring placed something like this. What about this? Is the magnetic flux 0 over here or non-zero? Is the magnetic flux 0 over here or non-zero? Tell me in the chats. Is the magnetic flux 0 or non-zero over here? Tell me, guys. See. This is a ring something like this. Understand very carefully. This is a wire. Place your thumb along the direction of current. Then curl your finger. So this is the direction of magnetic field. Like over here. This is the direction of magnetic field. So can I say in this particular case, this is the direction of magnetic field. So magnetic field is also creating some sort of loop over here. Okay, like if it is like this, so we say magnetic field is something like this. This is the direction of magnetic field in a loop, circular loop. But here, magnetic field is not crossing it. Like if this is a ring, if we have to cross the magnetic field through it, then the magnetic field should go like this from top to bottom, But it is basically creating a loop over here. We say here also magnetic field lines are not crossing the ring. Magnetic field lines are not crossing the ring. Okay, we say they are forming the loop. They are forming the loop. So I can say in this particular case, net magnetic field is 0. If magnetic field is not crossing, so magnetic flux in that particular case will be 0. Guys, tell me in the chats. Give me the signal in the chats. Is this clear? Is this clear? Everyone means everyone. Is this clear? Is this clear? Is this clear? And you guys are supposed to tell me the answer of this particular question. Everyone means everyone. Everyone means everyone. Everyone means everyone. Come on, tell me the answer of this particular question. Guys, see. The question here is given that we have got a ring, okay? We have got a circular ring. In this circular ring, current I is flowing, okay? In this circular ring, we say current I is flowing. And there is a squared loop over here which is present at the center, such that length of the square loop is much less than the radius. Means it's a very small loop. Sir, why you have shown it something like this? In order to make you understand. Okay, it's a zoomed view. But in actual reality, if this is this is the square over here, very small square. Okay, that's what does it actually mean. L is much less than R. We are supposed to find the flux through the ring. Guys, see. Let me just tell you. Because of this circular ring, we have studied that if we have got a ring over here, we say because of the ring, we say magnetic field is produced at the center. If you remember, I have told you, if we have got a ring, okay, if we have got a circular loop or ring in which current I is flowing, sir, whenever the current flows through a wire, it creates magnetic field. Here, I current is flowing through the magnetic field. We say at center, magnetic field because of the ring will be, that is mu naught I divided by 2R. If you remember, magnetic field because of this ring at the center is mu naught I by 2R. Now see, I'll write the same statement over here. I say as we say magnetic field due to a circular ring at center, that is B is equal to mu naught I divided by 2R. Sir, I is the current, R is the radius of the ring. Now, how to find the direction? Curl your fingers along the direction of the current. Thumb is pointing outwards. And here in this particular case, it is outwards. Outwards, we represented something like this, dot, outward. Okay. Now, this outward magnetic field is crossing this square loop. Now, guys, let me write over here. We say this magnetic field is crossing the square loop. This magnetic field is crossing the square loop. If this magnetic field is crossing the square loop in the outward direction, something like this, we say, so flux is produced. What is the value of that flux, sir? Flux is simply, that is magnetic field into area. Magnetic BA, and we say, sir, cos of theta. BA cos of theta. What is the value of theta over here? Magnetic field is in the outward direction. Area of the loop is also in the outward direction. So theta in this case is 0 degrees. Okay. So cos 0 will be 1. So here theta is equal to 0 degrees. So magnetic field in this case magnetic flux in this case will be B into A. Now guys, can I write it something like this? So magnetic flux is, what is the value of magnetic field? Mu naught I by 2R. So I'll write over here, this is mu naught I divided by 2R. Okay. And what is the area of the loop? We have to consider the area of the loop. So area of the loop will be simply, sir, length into breadth. So length is L, breadth is also L because there's a square. So L square. So that will be L square. So magnetic flux will be mu naught I L square divided by 2R. Guys, is this crystalline clear? Please give me the signal in the chats. Everyone means everyone. Give me the signal in the chats. Is this crystalline clear? You have got the next question in front of you. Please solo it from your end. I want you guys to let me know the answer in the chats. I would want you guys to let me know the answer in the chats. You have got a square loop. This is a square loop. And current flowing in the square loop is I. Length of the square loop is L. And there is a ring present at the center such that radius of the ring is much less than the length of this, because this is important, because we know this will create the magnetic field at the center. So at the center only this loop should be present. So that's why we say in this particular case this condition is necessary. We have to basically mention this particular condition. Come on. I would want you guys to let me know in the chats. Guys, see. Everybody of you, I would want you guys to understand over here. We say if the current is flowing through the square loop, we say here magnetic field due to a square loop is, here magnetic field due to a square loop is, we have studied if the current is flowing through a square loop. Remember, those who have not studied, if the current is flowing through the square loop, it will create the magnetic field. So we say magnetic field because of this square loop at the center. Sir, that magnetic field will be 2 root 2 mu naught I divided by pi into L. Sir, 2 root 2 we know. Mu naught is the permeability. Mu naught is the permeability. Directly remember over here. I is the current in the loop. Pi is pi. And L is the length of this loop. This is the magnetic field. Now, this magnetic field, how to find the direction of this magnetic field? How to find the direction of this magnetic field? Place your thumb along the direction of current, okay? And then curl your fingers over here. It is pointing inwards. Like here, the direction of current will be something like this, okay? I want you to place your thumb along the direction of current and curl over here, magnetic field is inwards. Now in this wire, current is something like this. Place your thumb along direction of current, curl your fingers, so it is inwards. It is inwards. And this magnetic field is crossing the loop. This magnetic field crosses the loop. This magnetic field crosses the circular loop. So we say flux is being produced. So what is the value of that flux, sir? Magnetic flux is simply, that is magnetic field into area, cos 0. Value of cos is 0. That is cos 0 is 1. Magnetic field we got, sir, magnetic field here is 2 root 2. Then we say mu naught I divided by, we say pi into L. And then we say area. Guys, we have to take the area of the loop. Could you please tell me what is the area of the loop, sir? Area of the loop will be simply, that is pi r square. Pi r square, it is capital R mentioned, so I'll write pi capital R square. So I'll mention over here, that is pi capital R square. Guys, is this clear? Please tell me in the chats. I hope you are loving the class. Someone is saying, I love this class. You have to. Is this crystalline clear? Is this crystalline clear? Next, my dear friends, let's suppose we have a coil something like this. We have a coil something like this, coil of many turns. And this coil is what we call the solenoid. This coil is what we call the solenoid. It is the coil of many turns, okay? You might have seen this, okay? Coil of many turns, okay? Solenoid. Okay. See. Don't say angle is 180. Let's suppose if you have got this coil over here. Its direction of area can be this also. Its direction of area can be inward also. It depends upon you which one do you like. You can take the inward also. You can take the outward also. Because direction of area is perpendicular. Now, tell me. Guys, tell me one thing. If this is a solenoid, okay? This is a solenoid coil, something like this. And we say, let's suppose current is flowing in the solenoid. We know that. Let's suppose if this is the solenoid and current is flowing in the solenoid, we know that it creates the magnetic field that is something like this. Along the axis. This is the solenoid. Magnetic field is along the axis. Guys, feel it. This is the solenoid. Magnetic field is along the axis. Now, if you take a sheet and place over here, if you take this rectangular sheet, place over here, we say this is the magnetic field. Guys, you are placing that this is the sheet. These are the field lines. Tell me, are these field lines touching it or these field lines are crossing it? Are these field lines touching or these field lines are crossing? Are these field lines touching or crossing? We can clearly say, sir, if we place a sheet over here, we said these field lines, these magnetic field lines, these are just touching the surface. We say here, inside the solenoid, we say field lines are not crossing the rectangular sheet. Field lines are not crossing the rectangular sheet. So we say flux will be 0. No flux is created in that particular case. Why? Because no field line is crossing. If no field line is crossing, means flux in that case will be 0. Means flux in that case will be 0. I hope this question is also clear. I hope this question is also clear. We have got this question. This is an important question. This is an important question. Okay, this is a next level question. I want to show you all the levels over here. That's why I have put up this next level question in over here. Come on. I would want you guys to tell me the answer of this particular question. Find the flux through the square loop. You have got an infinite wire. We say current I is flowing in the infinite wire. At a distance, there is a square loop present, a rectangular loop present. You guys are supposed to tell me what is the flux through the square loop. It's a square loop. It's not a rectangular loop. It's a square loop. You guys are supposed to tell me what is the flux through the square loop. What is the flux through the square loop? Can you guys let me know in the chats? Guys, see. We say here we have got this wire. This wire will actually create the magnetic field over here. This wire will actually create the magnetic field over here. Listen to me very, very, very carefully. This wire will actually create the magnetic field over here. And guys, I would want you guys to hit the like button as soon as possible. Hit it. Come on. Now, we say because of this wire. Guys, see, we say because of the infinite wire. Because of the infinite wire. Can I say magnetic field is? Could you please tell me what is the magnetic field because of the infinite wire? Sir. We say because of the infinite wire, magnetic field is mu naught I divided by 2 pi r. R is the distance. Guys, see. In this particular case, we say magnetic field because of this wire at this point will be something. Place your thumb along direction of current, curl your fingers. So here magnetic field is inwards, here magnetic field is inwards, here magnetic field is inwards, here magnetic field is inwards. So this wire is creating the magnetic field that is crossing this loop, How to find the direction? Place your thumb, curl your fingers, it is inwards. Now, we say here magnetic field is variable. Why? Because at this point, value of R is this much. This R is having some value. At this point, we say here magnetic field will be different. Why? Because from here to here, R is different. So here R is different at different points. Because magnetic field varies with R. If you increase the value of R, as you go from away from the wire, magnetic field decreases. Okay. Guys, so we say here magnetic field is variable through the loop. We say here magnetic field is not constant through the loop. Why? Because at this point magnetic field is more, at this point less, it keeps on decreasing. Now, what we are supposed to do in this particular case is, I want you guys to basically take a small strip over here. Okay. And we say, let's suppose the width of this strip is dx. It is extremely small, so let me take the width of this strip as dx. Okay. And this strip is at, let's suppose, what distance from the wire? That is at x distance. Guys, see, magnetic field through the complete loop is changing, different. But magnetic field at one point, this is one point, at this distance, x distance, is constant. Now can you tell me? We say as magnetic field at x distance from the wire from the wire. Magnetic field at x distance from the wire. That will be simply, we say this magnetic field is simply, that is mu naught I divided by 2 pi, mu naught I is the current, 2 pi, and what is the distance? 2 pi x. Okay. Now, this is the magnetic field at this particular point. Now, guys, tell me one thing. What is the direction of this magnetic field, sir? That is inwards. That is inwards. That is inwards. So we said this magnetic field is crossing this strip over here. So if this magnetic field is crossing this strip, small strip, don't you think that small flux will be produced? We say here, through the small strip, we say small flux is produced. Small flux is produced. And guys, how do we write the flux? Sir, we write flux as phi. And since through the small strip, small flux is produced, so we write this as d phi. So d phi is equal to, flux is equal to magnetic field into area. What is the magnetic field, sir? That is mu naught I divided by 2 pi x into area. Area of what? Area of this strip, not the entire loop. I'm talking about the flux through this strip. So area of this strip is what? Length of the strip is L, breadth is dx, so that is L dx. So this is the flux. This is the flux through the small strip. But we have to find the flux through the entire loop. Now, guys see. I'll write over here. To find the flux through the loop, to find the flux through the entire loop, I would want you guys to find the flux through the entire loop, we integrate. So I'll write over here integration of d phi is equal to integration of, we say mu naught I divided by 2 pi x, we say mu naught I divided by 2 pi x, then we say L dx. Now guys, the question is, from where to where we have to integrate? Guys, see, we say the first strip will be at a distance from the wire. Here is the first strip. And last strip will be at over here. So from here to here we have to integrate. Then only we can cover the entire loop. Over here. So we say we have to integrate from A to A plus L. L is the length. So we say it is from A to A plus L. I hope I'm not confusing you. I'm clearing every single point. Okay. Now guys, tell me in this particular case, what all are the constants? Sir, integration of d phi will give you the total flux. So we say this is phi total flux through the loop is equal. What will come out? We say, sir, mu naught will come out, current will come out upon, then we say 2 pi x is variable. Why, sir? Because for this x is a, for this x is something else, for this x is a plus L. So I'll write over here, and L will also come out, then integration of a to a plus L, and then we say 1 upon x, only it remains 1 upon x, and then we say dx. Now guys, what is the integration of 1 by x? Can I say, sir, phi total in this particular case is, mu naught I L divided by 2 pi. Mu naught I L divided by 2 pi. What is the integration of 1 by x? We say, sir, it is log of x. Okay, log to the base ex. Okay, and I'll write it something like this. We say limits are from a to a plus L. Limits are from a to a plus L. limits are from a to a plus l. Okay. Now, put the upper limit, then put the lower limit. That is a plus l minus a. Then we can say log of a minus b is log of a by b. So, final answer in this particular case will come out to be, I'll write over here, we say phi total will come out to be, that is mu naught IL upon, we say 2 pi. And then we say log of, I'll write over here, a plus l divided by a. Guys, please tell me in the chats that this is crystalline clear and you loved the today's session. And I would want all of you to hit the like button, okay? And I would want you guys to tell me later on, once I end the live stream, how was the session? I would want you guys to put up in the comments how was the session, because I have to see did you like it or not, because we keep on seeing your comments, reading your comments. I would want you guys to tell me in the chats later on. Not right now, but later on, my dear friends, okay? Because that is necessary and mandatory. And let me just tell you, my dear friends, that is, since this was the first class of Phoenix batch, Phoenix Pro batch, okay? And if you have not joined the Phoenix Pro batch as of now, okay? If you have not joined the Phoenix Pro batch as of now, I would want you guys to join as soon as possible, okay? Because see the level of content that we are providing. See the energy that we are giving in this particular batch. So it is just for 4,999 rupees. This was the first class. The link is in the description below. Click on to that link and buy this particular batch, okay? And most importantly, there is Unacademy Pro. My dear friends, when it comes to the Unacademy Pro, there is Plus, Iconic and Pro. This is the difference between Plus, Iconic and Pro. Like, these are all the features you'll get. A lot of students want to learn online, but they want to give the test series offline. That is possible with the help of Unacademy Pro. If you take it, you can go to the nearest center of Unacademy. You can give the offline test series over there. You can go for the revision classes in the offline. You can go for the offline doubt solving also over there. Teachers will clear your doubts and other features also. And most importantly, guys, I would want you guys to join the Phoenix Pro batch because you guys know it, okay? So that's all for today. So thank you so much, my dear friends. Okay? Wasim sir will be joining now, okay? You guys go over there and hit the like button. Join the Wasim sir session, everybody of you. Now he will be live on this channel only. The link is already pinned in the chats. You can see the link of the electrochemistry at sharp 7 p.m. So join this particular session, okay? So take care and bye-bye. Do let me know later on in the comment section how was the session. Thank you so much. Take care and bye-bye. Thank you so much.